Alright, so welcome to survey of PChem. We are going to start out with lecture 1. Let's derive the perfect gas law. Perfect gas law is ideal gas law. So you probably have seen these things, the PB equal nRT in the general chemistry 1. So we are going to derive this one for this short lecture here. Before I do this, let me try to explain the temperature and volume and pressure, because it's kind of important to actually have the good physical intuitions about the temperature, volume and pressure. So let's start out that one. The temperature, starting out with the temperature to me determines the average kinetic energies or average speed. So let me just try to actually write out something here. The kinetic energy is always 1/2 mv squared, the velocity here, right? So you can actually think of it as a velocity as a speed too, right? So if the kinetic energy goes up, the speed is going to go up, or velocity goes up, right? So it's more or less like 1-to-1 here. And as soon as you actually fix the temperature, the system or the particle tend to have one speed that's on average. And I have to emphasize that I'm talking about average kinetic energies or the average speed, because in the system like this, there are some particles actually traveling super fast and then some particles are traveling really slow. So individual speed may vary, like slow speed to the high speed, but on average, if you fix the temperature, then the average speed of the particle is actually can be determined, or the average energy of the particles are determined, given the same mass here. Each of these particles are like the molecule shown here, and you can think of this as a particle, or the molecule as a particle, and then that's one of these dot that's moving around here. And inside of this particle or the molecule, there is an atom just moving around, and the atoms are moving with respect to the center of mass of this molecule, but we're not really interested in that portion here. But I want you to think about this the movement of the particle here. The volume, by the way, has no explanations. What you see is what you get. It's the small volume, and it's large volume. You already have a good intuitions about that one, so I don't really care about that. Now the pressure, I have to explain this one a little bit more. So the pressure by definition is the force per unit area applied in a direction perpendicular to the surface of an object. So if I'm actually interested in the pressure that's acting on this wall right here, then the direction that matters is that directions only. And each of these particles will have the elastic collisions. That means that particle just bounce backwards, right? So the speed doesn't change. Incoming particle having the 100 miles per hour is going to bounce back at 100 miles per hour. The kinetic energy is conserved. And some particle is actually moving fast, will actually apply a little bit more force to the wall, and then there's a particle moving, the slow moving particle is actually give a little bit of a push, right? So the speed matters, and then also the number of particles matters too, right? So if more particle is actually hitting the wall, then the force applied on the wall is large. But if you have only a small particle hitting the wall, then the force applied on the wall is going to be small. So what it matters here is the number of collisions and then the speed. The partial pressure, it's kind of out of place to actually explain the partial pressure here, but let me just try to explain this one because there is not much of other place to actually explain this one. The partial pressure, you have already seen these things in general chemistry 1. The partial pressure is equal to the mole fraction multiplied by the total pressure, right? So for the partial pressure of the oxygen is equal to the partial pressure of oxygen is equal to mole fraction of O2 multiplied by the total pressure, right? So if we are living in a 1 atm environment, then the partial pressure of the oxygen is actually 0.2 atm because the mole fraction of the oxygen, as we know, is 20% of the whole air, right? So let's just go back to the previous slide. So if I actually look for this red dot right here, red dot may be the oxygen molecule, and then blue dot right here is the nitrogen molecule. The force applied by the oxygen molecule is much less than the force applied by the nitrogen molecule here, right? Because the number of collision, that frequency is much lower than the nitrogens. So that explains this mole fraction, which multiplied by the total pressure to give out the partial pressure. All right. So I've been actually telling you about this average speed or the average kinetic energies, but how do I actually get those distributions? So the distributions, for example, if you actually have the speed gun of that some sort, right? And then that if you have the particle just moving all over the place, you can actually record the speed of each particle by hitting with the laser gun or something, right? Then you can plot out how many, what percent of the particle actually having the velocities of less than 5 miles per hour, and then what percent of the particle are moving at 5 to 10 miles per hour, and then what percent is moving at 10 to 15 miles per hour, and so on and so forth. Then if you can actually plot out something like that, you get something looks like this, and that's pretty much it always happens to have speed distributions that looks like this. So the speed distributions or the velocity distributions is actually given by this formula right here. What's important here is that b square and then b square and then whatever the constant that comes in front. So what is the distributions? The distribution is a little bit difficult for me to actually explain these things, but I'm just too lazy to actually write out the whole thing here. But if I integrate the f of x dx, then it has to have end up with the area of 1 here. Then we call that f of x as a distributions. And sometimes that the distribution function may look like this for this particular case, which is x or speed, and then this is a population here. So somewhere around this speed v0, you have many particles moving at that speed, and for the v1 right here, you have a very small amount of the molecule moving at the speed of v1 here. That's what it means by the distribution here. So let's just try to see what's the property of the distribution here. If I have the low temperature, the majority of the stuff is actually moving at low speed, and then if you have the high temperature, the system is in the high temperature, then most of the stuff is actually moving at higher speed. And you notice that there is a mass term here, the mass term here and mass term here. I'll just try to erase those guys. So this distribution is mass dependent as well. So if the mass is heavy, then heavy stuff or the large particle is actually traveling super slow, most of them. And if you have a small particle or the light molecules, then most of the stuff is actually moving at fast speed. That all comes from this equation right here. So another stuff that I should probably mention is that some of the stuff that we talked about in the PChem actually comes from this distributions. It's called Maxwell-Boltzmann speed distributions, and that's why it's kind of important. And we're gonna use that formula to derive the ideal gas law. So how do I actually calculate the average of something? So if you already have the distributions, then all you have to do is distribution multiplied by the something and then integrate over the entire space. Then you can actually get average. So for example, if I'm interested in the average value of x, then all you have to do is just put x in front of the distribution and then integrate. If I'm interested in the average value of x squared, then I just need to put this x squared in front of the distribution and then integrate. That's pretty much all I have to do. So let's try to do something a little bit more useful here. So in the 3D space, or the three-dimensional space, the speed is actually given by the bx squared plus by squared plus bz squared. That's the speed along x directions, or speed along the y direction, speed along z directions, right? If you square them up and then add it up, and then you get the speed here. I'm just going to try to write something here. It's more likely that I'm going to give you the not very good pictures here, but let's just try it anyway. X, Y, Z, right? And then I have this 3D vector here, and then that vector right here has a x component, y component, and then z component. So that's the x component, y component, and z component. Then that one right there is the x squared plus y squared, right? That's the z. That's not it. That's z here, and then that's a square is actually this one, right? And then that this one right here, I call this as a b square is actually equal to a square plus z square, which is x square plus y square plus z square, right? So that's pretty much what's going on here. The speed of something is equal to the speed in x direction squared plus speed in y direction squared plus speed in z direction squared. Now, there is nothing special about this x or y or z directions, right? So I can actually put these things as a 3bx squared because x or y or z is pretty much the same stuff. Then let me just try to calculate the speed distributions. So this is speed. So if I actually write these things, if I'm interested in the speed square, then all you have to do, or that's actually try to put these things in the b square, then all you have to do, just like this one, is that I put b square in front of the distributions and then just integrate, right? That's pretty much all I have to do. That's average speed. Now b right here is actually equal to, let me just try to check this one, m over 12t. So if you put that the m over 2rt in this b right here, then that's pretty much what we have. So if you calculate this one, you end up in one of these guys. Now I think I should probably write out a little bit more about this stuff here. I'm sorry that the garbage truck is actually collecting the garbage outside. Alright, that's good enough. And so gas constant, if you recall that we have a 8.31 joule per mole. That was gonna be Kelvin here or something like this, right? Then, I think it's this one. But that what's important here is that it's a per mole quantities. So then if I multiply the Boltzmann constant by the Avogadro numbers, this is Avogadro number, so it's 6 times 10 to the 23, then multiply by the Boltzmann constant. Just look it up on the, using the Google. It's a very small numbers. Multiply that, then you actually get the gas constant here. And so does this M too. So that's the molar mass is equal to Avogadro number multiplied by the actual mass of the molecule. The molecule multiplied by the Avogadro number is going to give you the gram per mole quantities, right? So Kb over m, it's Kb over m, R over m, that, right? Because Na is going to cancel. So these two are exactly the same stuff. Let's just work on the per mole quantity, which is that one right here. So what we have here is that we have a speed is equal to 3RT over m. That's a three-dimensional space speed. Alright, so let's go back to the definition of the pressure. I talked about the definition of the pressure being the force per unit area applied in one direction, perpendicular to the surface of an object, right? So pressure is equal to force per unit area. Force, by the way, by definition, it's a momentum change of momentum in unit time, or the change of momentum over the change in time, right? So the how can I actually calculate this guy? So let's just calculate the momentum change first. As I said before, the number of collisions and then the speed matters, right? So how do I actually get the number of collisions during the time interval t? The first term right here, that's the density here. So n times the Avogadro number is just the number of molecules, right? Divided by volume is going to give you the densities, number densities. So the first term right here is the number densities. It's a number density. And then what is this term right here? That's area multiplied by the velocities times the time interval. Velocity times time, which is just the distance, right? So area multiplied by the distance is going to give you a volume, that, right? And then inside of this volume multiplied by the densities, you can actually get the number of particles here, right? Inside of this volume. And half of these guys are moving to the right, half of these guys are moving to the left, right? But only the one that's moving to the right is actually hitting the wall. So if you're interested in the frequency, collision frequencies, you only care about half of these guys. That's why I have divided by 2 here. So this portion right here is going to give you the number of collisions during the time interval t. And each time that the molecule actually collide, the particle is going to move that way and then bounce back, right? With the speed of v and then minus v, right? So what's the momentum change? Momentum, I'm going to use the little p right here, is mv, and then change in momentum is actually equal to the 2mv, right? Because the velocity changed twice, positive v minus the negative v, right? So the change in momentum is 2 times negative vx in the x directions, right? So that's the momentum change during the time interval t. If I actually divide the whole thing by delta t, just clear up the stuff somewhere around here, the delta t is going to cancel, right? And then the definition of the pressure is the change in momentum divided by the time interval divided by the area. So that area is going to cancel too. So eventually the pressure is actually equal to these things right here. Pressure is actually equal to these things right here. Alright, so we're going somewhere. Note that I should probably mention that this bx squared, that's in one direction, right? That the one direction is the only thing that matters. So P is equal to n times the molecular weight, the molar mass, multiplied by the speed in x direction squared divided by volume, right? And then also we have derived that the speed square is equal to 3 times that of the x directions, which actually comes from that one right here, right? The speed is actually equal to this one, so the speed square, actually this one, speed square is actually equal to 3bx squared, right? So, and then that's each speed is actually given by that one, right? So I think I went a little bit too far, but it's that the c squared is actually equal to 3bx squared. So plug this bx squared, that's the, let me just put this things, bx squared is actually equal to c squared divided by 3, right? So this one become that one, right? And then now that the average speed in three-dimensional space was actually given by this formula, right? That's the 3RT over m. That was the speed, right? And then put that things into here, then what do we get? You actually get PV equal nRT. So we have derived the ideal gas law. So that you may be wondering, so what's the use out of these things? The purpose of the PChem somewhat is that trying to explain how you get that equations. So now we know how to get the ideal gas law. That's the end of the lecture 1.